Okay.
Okay, folks, hear us on Zoom? Okay.
Okay.
All right, I think we can get started. So it's a pleasure to have our own Manu give the Astro Colloquium today. Manu received his PhD from Princeton in 2017. He was then a Chamberlain Fellow at Berkeley through 22. And since then, he's been a staff scientist over here at SLAC. He works in understanding large-scale structure at the intersection of galaxy surveys and CMB. He has famously proposed several techniques to reduce Rubin systematics using CMB. And today, among several other things, I'm hoping we'll hear about one specific one, which is understanding and correctly characterizing the baryonic contribution to small-scale matter. Fun fact about Manu, he's a DIY amateur astronomer. He's built his own Dobsonian 10-inch, including hand polishing the 10-inch mirror on it. And then just last week, I discovered that he also does radio astronomy. He showed me a plot that he made detecting the Milky Way spiral arms using his own radio telescope that he built in his backyard. And so then I said, okay, I will take you to the telescope next time when we're working on it.
Thank you very much, Zish, for the kind introduction, and thanks a lot for this opportunity to speak. I do aspire to one day becoming a professional astronomer. Yeah, I'm really delighted to have the chance to present to you even just a small fraction of the amazing work that the junior scientists in my group have been leading in the last few years. And for me, preparing these slides has been a chance to look back on my time here at SLAC and KIPAC, but also to look forward and think deeply about the direction that I want to set for my program, my group's research, and beyond. So today, my hope is to share with you my vision for where cosmology is going and where we can take it in this coming decade, which is really the decade of Rubin and CMB, Rubin and Simon's Observatory. And I think specifically here at SLAC and KIPAC, there's this tremendous convergence of opportunities for us. And I think if we move decisively, we can take this field of cosmology from the current intriguing heats and tensions that we see toward actual discovery for dark energy, neutrino masses, dark matter, and inflation. So I got really excited putting these slides together, and I hope by the end of it, you'll be able to see why. But to give you a little teaser, let me just say that if you really love your LSST galaxy and you want to learn all about it and all from it, you really should put it in the microwave. All right. So to get us started, here's my brief review of cosmology and the history of the universe with this timeline here. And what you can see here on the left is the Big Bang. And all the way on the right, 14 billion years later, is us today, right now, in this room. Now, there's a lot we know about the composition, the history, the evolution of the universe from many different probes. But for the purposes of this talk today, I'll be focusing on two classes of observables. The first one is this cosmic microwave background, the CMB. This is the first light that we see from the Big Bang. It was emitted only 400,000 years after the Big Bang. And when you look at those degree scale hot and cold spots in the CMB, what you're looking at is the baby picture of the universe. So for the purpose of this talk, this really is a picture of the initial conditions, the statistical properties of the initial conditions of the early universe. Now, all the way on the right, closer to us, is the large-scale structure of the universe. And that is the clumping of galaxies and matter in the universe. And you can think of this as snapshots at different epochs closer to today. These are basically the final conditions of the universe. And so a lot of the game of cosmology has been to try to match the statistics of the initial conditions as seen from the CMB with the statistics of the final conditions as seen from the large-scale structure. And if you're able to match them, if you're able to find a way that evolves the initial conditions into the final conditions, you may have a good model for those 14 billion years of evolution under gravity. You may have a good model for the universe. Now, it turns out we do have such a model, an extremely simple and extremely successful model that has predicted a number of observables, way more than I'm showing here on this plot. However, this model relies on dominant components of the universe, which are not part of the standard model of particles. So dark energy, responsible for the accelerated expansion of the universe. Dark matter, this dominant component of matter, 5 times more abundant than the ordinary matter. And inflation or whatever process is responsible for generating the initial conditions we see in the scene. And for this reason, I think really of cosmology and of the universe as a laboratory for doing fundamental physics, for doing physics beyond the standard model. And in many respects, you might think that the universe is the worst possible lab you could dream of for doing physics because it's a place where you cannot turn the knobs and rerun the experiment. But there's one thing for which it is the very best lab we have out there, and that's when it comes to gravity. So gravity, that weakest of all forces, but a relentless one, a long range, it sees everything, only positive charges, it adds up everything in such a way that all of these components that we don't see through any other interactions, we see through their gravitational impact when we look at the larger scales of the universe. And in fact, in the coming few years, there's a lot of prospects for learning about these components. What is dark energy? How much energy is there in dark energy? How does it evolve in time? Which we call the equation of state of dark energy. What are the particle physics properties of dark matter? Does it have interactions? What is its thermodynamics? And what is the particle physics of inflation? How many fields? What are their interactions? What energy scales do they operate? And the way to answer these beyond standard model physics questions using cosmology is by probing their gravitational impact, the gravitational impact of these components on the expansion history of the universe, so the background geometry of the universe, and on the growth of the fluctuations. Okay, so universe as a fundamental physics lab for probing beyond standard model physics. Another example of beyond standard model physics that we can probe using cosmology is that of neutrino masses. So neutrinos are the second most abundant particles in the universe, second only to photons. And yet there's a lot we don't know about them. We don't know their exact masses, the ordering of these masses. Are neutrinos their own antiparticles or not? Are there additional species? And is there CP violation in the neutrino sector enough to explain the matter-antimatter asymmetry? And once again, the universe is a good lab for neutrinos because we know from oscillations that they comprise at least 0.5% of all the matter today. And because gravity is relentless, this 0.5% of all the matter has actually been pulling on all the rest of the universe since redshift 100. And this results in a much larger effect on the large scale structure, 4% effect. This is illustrated here. If you compare a universe without massive neutrinos or with massive neutrinos, you see that the clumping of matter on small scales is erased. And that's one of these effects, 4% effect, that's actually within reach of upcoming experiments. So forecasted precision of 20 electron volts, and that's a 3 sigma measurement for the minimum mass scenario with upcoming experiments. Okay, so learning about dark energy, dark matter, inflation, neutrinos from cosmology by combining or comparing CMB and large scale structure in terms of the expansion history and the growth of structure. Now, I would argue that this coming decade is actually an incredible one for doing this kind of work. And that's because of the arrival of key large-scale structure experiments. And I don't need to tell you about Rubin, but I still will. The dark energy spectroscopic instrument has been extremely successful so far in producing catalogs of the 3 positions of galaxies, tens of millions of galaxies. It will be continuing with this extension, this 2, and perhaps Cyclus 5. The SphereX satellite was just recently launched with the goal of mapping the universe on the larger scales with low angular resolution to probe primordial Gaussianity. But the exciting part for me and for us here, I think at SLAC and KIPAC, is the start of the Vera Rubin Observatory. Now, I and my group have contributed to these experiments through analyzing data, producing new methods for DISI, building a significant part of the cross-correlation science case for SphereX, and producing a number of methods for Vera Rubin. And I'm excited that we're finally going to be able to apply all these exciting methods to Rubin data. Now, if you have been awake in the last few months, you surely have seen the first look of Rubin data. The data is looking incredible. the plan is to map the positions of not tens of millions, but tens of billions of galaxies in something like 2.5D. It's something you can do when you have mastery of the photometric redshift errors, like we do with Eric Charles here. And really here you are in the home of Slack, in the home of Rubin. Certainly you are at Slack. And what I'm trying to say by this is that Rubin is the dream child of a lot of people in this room. The thought process, the design for this experiment started more than a decade ago. And today, the team here at Slack has built the largest digital camera ever built for astronomy, placed on the telescope with 5 times more étendue or grasp than the previous generation of cosmic experiment. And the junior people at Slack and KIPAC are really running with it, taking over this experiment. And it's up to us to do a lot of great science with it. Now, this large-scale structure, this decade for large-scale structure is going to be dominated by LSST and Rubin, but it actually doesn't end there. On the cosmic microwave background side, the situation is also very dramatic with new experiments like South Pole Observatory and Simon's Observatory coming online. So I have worked my whole career on the Atacama Cosmology Telescope, the precursor to Simon's Observatory, and now Simon's Observatory. And people in my group have proposed a lot of innovative methods to analyze the data from ACT in Simon's Observatory, applied them to ACT, and we just can't wait to apply them to Simon's Observatory. To give you an idea of what Simon's Observatory means, if you haven't been following the CMB world in the last few years, this is the jump from Planck satellite ACT. And so here on the left, what you're seeing is those degree scale hot and cold spot that I mentioned, those initial conditions of the universe. But when you crank up the resolution by a factor of 5 and the sensitivity by about as much, what you see is not only the degree scale hot and cold spots, you actually start to see individual astrophysical sources. Emission from AGNs and dusty star-forming galaxies, and shadows from galaxy clusters that I'll tell you a lot more about it. So the point I want to drive here is that if you've been thinking of CMB as me without my glasses, very blurry vision of the early universe, really you should change your mind. We're actually starting to see individual sources, and the typical objects that you might actually be able to see in the night sky with your amateur astronomy telescope, you can image them now with CMB experiments. Okay, so that's the jump from Planck to ACT. What about ACT to SO? Here's a patch of a CMB map from ACT, collecting 5 years of data. You see again these blobs and the point sources. And here's the same map as seen by SO in 5 days. So there's some differences. This is preliminary data reduction, but 5 years to 5 days, that's a dramatic increase in speed. And so this is really going to be transformative data over half the sky, fully overlapping with LSST. And again, you are in the home of Simon's Observatory. A lot of people here, including Zish, Susan, and myself, have played key roles in dreaming this experiment, building the science case for it, actually building it and operating it. And I just can't wait to analyze this data. Okay, so the picture I've painted so far is we have these science questions. We have these amazing experiments coming online to answer these questions for us. So what's the problem? Why don't we just do it? And I would argue that there are challenges. And the question I want to ask is, are we ready for this dramatic improvement in data, this dramatic increase in statistical power from Rubin and from LSST? And the way I look at this question is by looking at current experiments. I've told you that we learn about dark energy, dark matter inflation in the neutrinos, comparing expansion history and growth of perturbations. If you do this with current experiments and you look at the expansion history or at the growth, what you see are those maltensions. So here on the left, what I'm showing in purple is the omega matter, the fraction of the energy density in the form of matter today as measured by the CMB, which you can compare with these contours in blue or orange as measured from these at times. And so what you can see is a mild disagreement between CMB and the large scale structure. And the same sort of situation holds if you look at the growth of perturbations. This has been called the S8 tension, so a disagreement on this parameter S8, which is a measure of how clumpy the matter is and how much matter there is. And if you compare measurements from the cosmic microwave background in blue with measurements from photometric surveys in green and orange, what you see is a slight disagreement again in those measurements. And the interesting thing about those disagreements between comparing CMB and large-scale structure is they do lead to important consequences when you're trying to infer physics. So results of these disagreements are the following. We have claims of dark energy evolving. So hints where the equation of state of dark energy, instead of being centered on this point up there, would be away from it, signaling that the dark energy would not be a cosmological constant. And connected to this tension is the constraints we're currently getting on the sum of the neutrino masses, where the measurements we're getting, these posterior curves you see here, actually prefer mass values quite a bit smaller than the minimum mass allowed by oscillation experiments. And so this is an intriguing situation. You know, have we detected evolving dark energy? Are we detecting neutrino masses below what's physically possible from oscillation experiments? These things can also be explained with curvature. They can be explained with an error in the optical depth from the CMB. They can be explained with systematics. They could be explained with early dark energy. So how do we learn something useful from there? How do we make progress? If this is systematics, how can we be sure that with much better data sets, we're not just going to be a lot more biased? So I think there's a real challenge here. And we're sort of at this pivotal point where we need to understand what's going on here, while at the same time, the data is getting a lot better. And if we're not ready systematics-wise to analyze it, this is going to be a challenge. But I would say this challenge is actually an opportunity. And so how to do trustworthy cosmology in the era of Rubin and Simon's observatory. This is the outline of basically my joint probe strategy, the program that I'm pursuing within my group here at SCI. The first point here, controlling astrophysics uncertainties. I have complete trust in my instrumental colleagues on understanding the instruments. And so I turned my attention to the other sorts of systematics, those that are not in your instrument, but are on the sky. And those ones you cannot fix by just having a better instrument. You need to understand their astrophysics. And so here, the question for me is, how can we disentangle the role of dark matter invariants? I'll tell you a lot more about this in a moment. This is a challenge for cosmic shear from LSST. This is also a challenge for foregrounds from the CMB. And I think this is a place where LSST and SO can help each other out in a way that couldn't be done with either of them individually. And the following points are what you can do if you're able to do this. Once you understand your LSST data and your SO data, what can you learn from it? The first direction that's important to me is breaking fundamental physics degeneracies. I told you that the current tensions could be attributed to evolving dark energy, non-minimum neutrino mass, curvature, etc. How can we get to a place where I can talk to my neutrino physics colleagues here at SLAC and tell them, no, this is the mass of the neutrinos. It's not model dependent. It's not affected by dark energy, etc. And I think this is a place where we can make progress. The other one is once we have these dramatically improved data sets, galaxy surveys from LSST and CMB maps from SO, is we have the opportunity to open a lot more windows onto the universe, a lot more probes that would be otherwise inaccessible. The first one for me is line intensity mapping, how to cover those 80% of the uncharted territory between CMB and large-scale structure, leveraging cross-correlations with CMB and galaxy surveys. And the others are a wealth of CMB effects that are as of yet undetected, but really borderline, and my group is working on. And finally, it's hard to imagine that 10 years from now, we will be doing cosmology analysis the way we're doing it now. It's very clear that we're moving towards integration with AI and towards field level inferences. So how can we get ready for this? So this is the strategy for my research program at the moment. And all of this hinges on combining CMB and large-scale structure, but doing so in a different way, with a different philosophy from what has been done in the past. And so I've told you that the CMB is about the initial conditions of the universe, and that's partially true. But really, for you to see the CMB, those photons have had to travel all the way from the early universe towards you. And along their way, a number of things happen to these photons. A small fraction of them are Thomson scattered by free electrons around galaxies. And in doing so, they imprint shadows on the CMB, shadows that tell you about this ionized gas, and reveal it much like you would reveal a watermark on a dollar bill in a way that you couldn't see by just looking at it. The other effect that can happen to your CMB photons is gravitational lensing, where their path is deflected by the gravitational pull from the logical structure. And finally, as you've seen in that ACT and SO map I showed you, you see the emission from astrophysical sources. So these are called CMB secondary anotropies because they do not come from the early universe. And both of these topics, shadows of the gas loosely and shadows of the total mass from lensing, are topics where my group here is really one of the world experts and leader. And having access to the data from LSST and SO puts us in a particularly interesting position to lead this. So going back to this strategy, because of time, I will only have time to dive into one of these topics. But I hope that the principle will be clear and how it generalizes to the others. And so I'll be focusing for the rest of the talk on this question of controlling astrophysical uncertainties, and especially baryons. And so my apologies for all the group members and their amazing work on all these topics that I won't be saying much more about today, but hopefully we'll be previewing some tomorrow. All right, baryons. Baryons, why do baryons matter? Where did the baryons go? So if you look at a hydrodynamical simulation of the universe, what you might see is the distribution of dark matter here in blue. And very soon you will see in green and red the distribution of the baryons, the ordinary matter, mostly in the form of gas. And while they may seem like they initially trace each other, clearly you're seeing all these fireworks, all these explosions in the cosmic web. These are the results of a supernova, a death of massive stars, and the accretion onto supermassive black holes, active galactic nuclei, which inject energy and momentum into this gas and redistribute it. In doing so, they regulate the process of star formation. They are effectively a feedback in the star formation loop, a negative feedback. And the amplitude of this feedback, or the modality of this feedback, is the largest uncertainty in galaxy formation. And so if you could locate or localize those diffuse baryons in the outskirts of dark matter halos, you would stand a chance to learning about feedback. To give you an idea closer to home as to what this looks like, I'm sure you have seen the Milky Way, the night sky, and one of our closest neighbors, the Andromeda galaxy. If your eyes could see not just the starlight, but the whole gas around the galaxy, the Andromeda galaxy would not span a few degrees on the sky, but more like 60 degrees. So there's a lot more to be seen than just the starlight. Okay, so baryons matter because they can tell you about galaxy formation. Another reason that baryons matter a lot, if you care about LSST and doing lensing from LSST, is that they have a large impact on the matter power spectrum and therefore the lensing power spectrum. So what I'm showing you here on this plot is the fractional effect on the lensing power spectrum, or cosmic shear power spectrum, as a function of angular scales, with small scales on this side. And the different colorful curves are what you get from very different hydrodynamical simulations with different prescriptions for feedback. What you can see is suppression of the matter power spectrum due to gas being expelled. And if you look at the span across all these curves, you see something like 30%. And what 30% means is that we basically know nothing about baryons. What do I mean by this? Baryons are 15% of the matter, and so at the power spectrum, which is the square of the field, it's a 30% effect. If you somehow made all the baryons in the universe disappear today, the matter power spectrum would go down by 30%. And so on the scale of individual halos, we basically do not know anything about baryons. I'm certainly oversimplifying, and I'll tell you a bit more about this in a bit. And so you have to contrast this 30% uncertainty on our modeling of the lensing power spectrum with the percent precision, which is the measurement target for LSST. So if you want to learn about dark energy from LSST, you need to measure this lensing power spectrum to percent precision. 1%, also 1 is minus 1% on this plot, is about the thickness of these curves. And you're contending with this 30% theoretical uncertainty. So clearly that's a challenge. Now, a silver lining there is because baryons are only 15% of the matter. If you want to reduce this scatter to total 1% on the total matter, you only need to know the baryons to 5% precision. And I will argue that this is already the precision we have. To give you an idea of what that looks like in current data, this is Dark Energy Survey year 3. All these panels are different correlations for cosmic shear. So this is the cosmic shear data set. And everything you see in blue is a data point that is being thrown out because we don't know how to model the variance. So it looks very sad to me that there's all this incredible data that we're just discarding because we don't know how to model it. And as the data gets a lot better with LSST, if you don't do anything, the blue areas are just going to grow up. So I would hate to see that. And I think we don't have to take this. I think we can fix it. Now, there are many powerful probes of baryons, each with their strength and limitations. And so I just wanted to list a few here. The first one is galaxy luminosity functions. So if you want to learn about feedback, which regulates galaxy formation, well, why don't you just look at galaxies and how their stars evolve? And so this is a direct probe of feedback in the sense of feedback in the star formation loop. But for learning about baryons, the challenge is start with only 1 to 10% of baryons. So this is sort of the tail wagging the elephant in terms of the baryon budget. The second one I want to mention is X-rays. And this is perhaps the richest probe that we have of the hot gas, its density, temperature, and many other properties in clusters, in groups, and even lower mass objects now with new data. And one challenge is the nonlinear scaling of your observable with density, temperature, and clamping, which reduces the need for some modeling. Quasar absorption lines or others, and in the future, fast radio bursts might be really exciting. But in this talk, I'll focus on one from the CMB, the so-called kinematic Sunyaev-Zeldovich effect. And I want to tell you why one would do this and why it's special. So the kinematic SZ is what happens to a CMB photon as it bounces off a moving electron in the hot gas around the halo. And this is a Doppler effect. So if your halo is moving, the CMB photon is effectively bouncing off a moving mirror, and its frequency changes. And so the size of the effect is about the optical depth, how opaque is your computer, and about how fast it is moving, so the velocity of the halo. And if you think you understand the velocities, then you have a measurement that's linear in the amount of electrons and therefore linear in the total amount of gas. So it's a key strength of the KSZ effect, this linearity in the gas density. And results from this are the fact that the KSZ signal does not depend too steeply on the density being nonlinear and does not depend too steeply on the halo mass. And so it's a good probe for the outskirts of halos and low mass halos. And because it's a shadow on the CMB, it sort of doesn't matter where you put the object, the signal strength is the same. And so this is a particularly useful probe for higher redshifts, the ones that you might care about for something like cosmic shear. And finally, the modeling of it is independent of temperature, metallicity, and cropping. And so in this respect, it seems particularly well suited for weak lensing where you care just about the gas density. And for learning about feedback, of course, it'll be extremely complementary with all the others. Okay, so that's the KSZ effect and why one would look into it. How does one measure this kinematic SZ effect? And here there's a number of challenges that actually turned out to be strengths. The first one is there's no spectral signature. This is a Doppler effect. It turns a black body into a black body. You cannot extract it away from the CMB. But the flip side is all the CMB maps that you've ever seen published are actually CMB plus KSZ maps. But more importantly, the second one, the velocity of object changes sign. Some objects are moving towards or away from you, producing a positive or negative KSZ effect. This is a challenge because if you just stack KSZ around galaxies, on average, you will get a cancellation and you will see nothing. But it's actually an opportunity because if you know the velocities and you can use those in your estimator, you can now selectively extract the KSZ because no other foreground changes sign based on velocity. And this is a key advantage over something like thermal SZ, for example. So how do we do this? It turns out a really good handle you can get on individual halo velocities is from this process called reconstruction. This is the same as in bioreconstruction. It just says by mass conservation, if you have more stuff here, it's because things have been moving in that direction. And that may sound simplistic, but it works actually extremely well. And once you have a large sample of galaxies with individual velocities in a CMB map, and then stack your CMB map at the positions of these galaxies, taking into account the change of sign, and extract the gas profile around your objects. This type of measurement is one that I pioneered, and my group is currently leading in terms of the precision and the control of systematics for these measurements. And to show you results from Bernalita Ritwachaya last year, the signal to noise in those measurements has been steadily increasing. And you might say, that's nice, but do I really care about slowly ramping up the signal to noise? The point here was this is very intentional because what we want is to reach the target for cosmic shear. So again, I want 1% on the modeling of cosmic shear. So I want about 18 or 20 sigma, 5% on my variant, which is the target here. So the goal really of this program in the last few years was, can we get the precision above this line? And what you can see is that measurements from older galaxy surveys and then DESI and newer DESI have steadily increased and followed a very simple naive expectation for how the signal to noise should go. If objects are more massive, more signal. If there's more of them, more signal to noise. And currently with DESI year 3, we actually are above this threshold. And the forecasts show that actually for LSST, things are going to get a lot better. So we have the sufficient precision for modeling LSST at the moment. And a key result in Bernie's paper is that data from LSST will actually be extremely useful for this, more than people had thought. The common wisdom was that you need spectroscopy to do those velocities and get this and get KSZ. What Bernie showed is that what you lose with photo-Z errors, you more than compensate with your sample size. So one photometric galaxy, one spectroscopic galaxy is worth 4 photometric galaxies, and you have way more than 4 times more galaxies in LSST. So I would say at this point, mission accomplished. We've turned this fledgling observable into a precision tool. The signal to noise is good enough, and so now it's time for us to turn our attention to the modeling. So the statistics problem is solved. Now we turn to the harder but also more interesting problem of how do we model this.
So I thought synapse Novich inside a galaxy or cluster, a small object, but you're using the mass distribution on a much larger scale. There's something I didn't know.
Oh, yes. No, that's a really good question. So I'm trying to measure the KSZ effect, which is about velocities and density of the gas. The density of the gas is on a very small scale. For a very large cluster, it might be a megaparsec. But so how can I extract the signal from the larger scales? Like we're looking at gigaparsecs here. And the key here is that there's a separation of scales. So the velocity field actually is coherent on hundreds of megaparsecs. And so that velocity field I can reconstruct from the whole survey. And so the random motion of your specific halos are actually small compared to the large scale motion. So from the larger scales, I extract the velocity. And then I know the exact position of my cluster. And so I let the CMB tell me the small scale gas density here. But that's a really good point. There's this key separation of scale.
And this is true even if there are larger variations in velocity within the cluster itself.
That's right. So of course, if I ask what's the motion of the gas in this cluster, one dominant component, order 300 kilometers per second. Actually, I shouldn't call it dominant, but there's the 300 kilometers per second, which is the large scale linear density, linear velocities, coherent on hundreds of megaparsec. If I look inside the motion, the thermal motions, inside of these clusters are much larger, and those produce that thermal IC. Then you may have some random motions, rotation or slushing inside your cluster. Those ones I'm not extracting in this method because I don't have an estimate for them. But that's not a concern for me when I care about the average profiles for modeling something like cosmic shear. Thank you. Okay, so the signal to noise is now high. How do we fix our modeling? And before I do this, just to show you what the data looks like, we're now able to produce result gas profile around galaxies across galaxy population, type, mass, and redshift. And so what I'm showing you here is some distribution for redshift for different galaxy samples from DESI. Bright galaxy survey, luminous red galaxies, ELTs, and within each of them, we can further split in redshift. Same thing in mass, and further splitting in mass. And we're able to produce those sort of cumulative gas profiles as a function of aperture for all these subsamples. And so probing a large range of mass and redshift will be crucial for using those data sets. And everything I'm showing you here uses DESI data. This will get a lot better with that. Okay, so modeling. what do we do with those measurements? It's nice to have signal to noise. It's nicer to learn something from it. And here I want to make a distinction between three different questions that are often lumped together in the literature. And the word feedback is often loosely used to refer to very different things. And I would argue that depending on what you mean by feedback, your approach will have to be very, very different. The first simpler problem, in my opinion, is what is the impact of baryons on galaxy-galaxy lensing? Stacking galaxy shapes from LSST around foreground galaxy positions. And this is a measurement of the total matter profile, dark matter plus baryons. The challenge is what are the baryons doing? And if you don't know their profile, you won't be able to model the dark matter. Now, I would argue this is the easiest problem because I can stack my CMB map and measure KSZ around the same exact galaxies. And so effectively, I'll have measured just the gas around these galaxies, and I can simply effectively subtract KSZ from lensing. So if your goal is to model galaxy-galaxy lensing, life is easy. I would argue this is a solved problem, and I won't say more about this. The second problem, which I'm more interested in, and I think is a lot more impactful for learning about cosmology, is the impact of baryons on cosmic shear. So the correlation of shapes with other shapes. And this tells you not about the mass profile around a specific galaxy, but the whole integrated distribution of all halos, of all masses and redshifts between you and the galaxies you're looking at. And the challenge here is much greater because your cosmic shear signal, the lensing power spectrum I showed you, cares about all these halos of different masses and redshifts. But our KSZ stacked galaxy profiles only probe a certain range of mass and redshifts. And so there's a question of extrapolation. Are you measuring the gas around some halos and then somehow having to guess what the gas looks like in halos of different masses or redshifts? That's a challenge. And the other challenge is our KSZ currently does not measure gas around halos, it measures it around galaxies. And so how do I connect my galaxies with their host halos? So these two questions, galaxy halo connection and extrapolation across mass and redshifts, are key challenges that my group is working on addressing right now. And finally, the third question, perhaps the hardest of all, is about astrophysics and how do these processes work? How do AGNs work? How do supernovae work? And I would argue this is the hardest problem to tackle. The first one is if you want to compare your measurements to hydrodynamical simulations, you have to make sure that the galaxies in your simulations match your real galaxy. And this paper, which should come out hopefully in the next week or two, shows that matching galaxies in reality and simulation is much harder than just one mean mass. And a broader question, if you're using hydrodynamical simulations, is there anything to be learned about feedback from hydrodynamical simulations? Hydro simulations have shown to actually lie in a 1D parameter space in the manifold of possibilities. And this is not a fact of nature, it's a fact of how these simulations are run. And so even if your simulation matches your data, are you sure that you've learned anything meaningful about feedback? And if you're using the scatter cross simulation to quantify your uncertainty, you may be grossly underestimating. So going back to this second problem of the impact of baryons on cosmic shear, this is a problem where I think we can really turn things around in the short time scale. You may have noticed that the literature on this topic has become very broad, with many papers attempting first steps in this. Many of these papers basically take the KSZ measurements that Bernardita produced and extrapolates them to a prediction for the matter power spectrum. I think these are exciting first steps. I think we need to make sure we understand that galaxy halo connection and the extrapolation across mass and redshift. And so this is the two problems that Bernardita is currently working to address. And our solution is to jointly forward model cosmology, halo gas profiles across mass and redshift, as well as the galaxy halo connection. And the idea is that what this lets you do is anything you will infer from this will be marginalized over your uncertainty in how galaxies and halo connect, and will properly propagate the uncertainty from gas profiles of halos you have not measured. Very many arrows on this diagram I made, but the story is really simple. Cosmological parameters predict the dark matter. From your gas parameters, you turn this into a gas profile. From your HOD parameters, you turn the dark matter in a galaxy catalog. From there, you can straightforward model all of your observables. So the cosmic shear that you're trying to model, the KSZ signal that you have measured. And you can use galaxy-galaxy lensing and clustering to constrain that galaxy-halo connection. So I think this is well defined, and I think this propagates uncertainties in a way that's robust and that I would trust further in cosmology from this. Okay, so that's one approach to this problem that we're pursuing. I wanted to flash a second one that I think is a really new and exciting idea that I hope to be able to tell you more about this very soon. This is work led by Anima Ganguly, which I'm co-supervising at Arizona with Elizabeth Krause and Tim Eckert. And the idea is, I've told you, the challenge is measuring KSZ around galaxies instead of halos, and not around all galaxies, not around all halos. What if we could directly correlate KSZ with shear? So if you could make a map of the KSZ, it would contain the gas profiles around all halos of all masses and redshifts. A map of cosmic shear contains the same thing with baryons and dark matter. If I could directly cross-correlate them, I would have exactly the baryonic contribution to cosmic shear. So this would be really ideal. Why have people not done this a long time ago? And the answer is that KSZ is not just gas, it's gas and velocities. And so if you don't know what the velocities are doing, your stack is going to be easy. But I think I have a new idea on how to handle this. The preliminary forecasts are looking promising, but ask me again in a few minutes. Finally, a third solution I wanted to bring up that's probably more futuristic is to use another CMB secondary entropy that I alluded to, this screening effect. I won't tell you much more about this. Feel free to ask questions. And I'll just say that the state of the art in this field has been pushed by the work of Theo, Abby, and Noah, who are in the group. So this is all I wanted to tell you about this direction of controlling astrophysical uncertainties in LSST using the CMB. I wish I could tell you more about the other topics, and I will flash some of this tomorrow during the KIPAC team. But how do we turn this sort of program or strategy into a reality? Here's my plan for the next 5 years, how to deliver precision and trustworthy cosmology from LSST and CMB. On the baryon side, as I've explained, I believe we can solve the issue of modeling baryons in LSST cosmic shear. I think this is extremely close. A really exciting possibility to actually learn about the astrophysics of feedback. And for this, it's very clear to me that KSZ alone won't cut it, and you'll need to join forces with other observables, including with all the expertise of the X-ray group here at SLAC and KIPAC. The second direction that I mentioned, and where I think we can make key progress, is to really clarify all the ways in cosmology in which neutrino mass sensitivity comes from. We have preliminary results showing an interesting twist on this story as to whether this comes from expansion, whether it comes from growth, the redshift evolution, or the scale dependence of growth. And so I think here we have the possibility to clarify what's going on and either produce neutrino mass constraints that are independent of dark energy or establish the conditions that are required for doing so. On the side of opening new observables, new windows onto the universe, thanks to these large data sets, we are extremely close to a first detection of 21 centimeter NCMB lensing, including with work from Tristan and Dylan that I'll say a bit more about tomorrow. And we're very close to first detections on these two effects, which my group is pursuing right now. So this would be really impactful for opening up high Z light intensity mapping as a large scale structure probe, and to be able to look at the universe in different ways, transverse velocities, direct map of the galaxy. And finally, when it comes to getting ready for the way data will be analyzed in the coming decade, I think something that we're perfectly well positioned to do in terms of experiments, data sets, and theory expertise is get ready for AI methods by producing the largest non-AI 3D reconstruction of all of these fields, dark matter, baryon, velocity, tidal tensor, etc., to serve as a benchmark for future AI foundation. This will have countless immediate applications in this direction, and I think we'll set us up for the future. Okay, so this was my 5-year plan. Looking a bit further in the future, thinking both about experimental opportunities, modeling, and what I'm hoping we will learn. I think after this decade is over and LSST is done, and perhaps after Spec S5 happens and is done, I think we will have to shift our strategy from building better, deeper surveys to looking at opening new windows onto the universe. Photometric surveys post Rubin with diffusion fusion limited from the ground, and spectroscopy from the ground post Spec S5 will probably reach the practical limits of what we can do there, including on the region. I'm very excited about what might come on the CMB in terms of R, and crucially for the CMB large scale structure program on the optical depth, the CMB with Lightbird. But beyond this, I think what will be really exciting is the possibility to make line intensity mapping work for the rest of the observable universe. There's real potential for progress in CMB secondaries beyond CMB Simons Observatory with something like CMB HD. And finally, I would love to see spectral distortion experiments probe the ultra-high universe and the ultra-small scales. In terms of analysis method, I think it's very clear that we will be combining all our surveys and data sets of different types. And it's very clear that this will happen not just on the scale of individual surveys, but at this point on the scale of the whole observable universe, given the size of these surveys. And I think AI will play a key role in this in many different ways. I'm really hoping we will keep improving on neutrinos beyond this decade, paralleling Gaussianity at high Z, dark matter and galaxy formation from the smallest scales, as well as the astrophysics of organization. So this is all I wanted to say. I just wanted to thank with a big thank you to the whole group, many of whom are present here or on Zoom. This has been one of the most rewarding parts of my job, and I think one of my proudest accomplishments here at Slack, building this group, and now really delighted to have Oliver join forces and bring a whole extra dimension to what we do here. So Slack and KIPAC have been an extraordinary environment for me, both scientifically in terms of growth and just as a community of people to work with. I'm excited to bring the newest generation to this research program, and I'll leave you with my summary. So this coming decade is really truly the Rubin SO and Rubin CMB decade. I think it's clear that progress on physics from cosmology will have to come from joint probes. And I think these thin joint probes, if we analyze them differently, will allow us to overcome those tensions and open up a lot of new windows in the universe. So using the CMB as a backlight for LSST to control its astrophysical systematics, LSST helping CMB with its foregrounds. And once this is done, I think thinking deeper about how to break physical degeneracies, making sure we can say we have actually learned about neutrinos or definition, unlocking new probes. So yeah, new ways of analyzing data. And I think we here at Slack and KIPAC are perfectly positioned for this, given our role in Rubin and SO, the expertise in X-ray, in KIPAC theory, EPP theory, and all the examples here. So I'll stop here and take any questions. Thank you for your attention.
Okay,
Yep.
Next was really nice talk, Manu. I'm curious about in the KSC whether you have to deal with like backgrounds and foregrounds messing you up. Like, are you ever worried that you have two galaxies on top of each other and you can't really tell which you're looking at?
Yeah, no, that's a really good question. And so there's a number of elements to this question. So backgrounds and foregrounds. One foreground, as I mentioned, the KSZ has the same frequency dependence as the primary CMB. And so the CMB is always a source of noise for KSZ. You are helped by the fact that the CMB varies on degree scales, and the gas signals from KSZ from your objects varies on arc minute scale. So you have this separation of scale. But as you look to multiple times the virial radius around your galaxies, the CMB becomes a large source of noise. And that's included in all of these measurements. In terms of other foregrounds that we usually think about for CMB, things like the thermal SZ or dust emission, this cosmic infrared background, etc., you are really helped by this changing sign of KSZ. And so when your estimator is looking for something that changes sign, really nothing else does. I say nothing else. Abby Manier and I did write a paper on Doppler boosted dust emission. So that's an effect, but we've shown that it's a very small contribution. So that's in terms of the measurement. And then you talked about overlap. Another way to frame this is two halo term. So the overlap for objects that are uncorrelated are not something that we have to worry about, but for objects that are neighbors, this is something that matters. And so when you see the whole gas profile around the galaxy, you're not just seeing the gas around that galaxy, you're seeing the gas around its friends as well. And this is something that this two halo term is something we're barely detecting right now. And so I think the accuracy to which we need to model it is not yet extreme, which is helpful. But we will have to think about it a bit more with your data. Thanks. Here and then lens.
Yeah, very cool. A lot of the digest, but about the predictions of ionic feedback improvements with LSST, did you account for the systematics in the photo estimation, or it's just a statistical uncertainties compared to the spectrum?
Right. I think this is a really good question of exactly how much better do you do? And I think there's several sort of like components to answering this question. So the common approach that has been used in state-of-the-art weak lensing experiments is twofold. There are skill cuts. So I just throw out all the data to the right of somewhere such that I think I don't have to worry about variance. This was the approach originally. So the statement was, thanks to this skill cut, you don't have to think about variance anymore. But the result is, despite those skill cuts, it appears that that's not the case. You still have to worry about foregrounds, just because the effect on the gas may have been larger than was initially anticipated. This is something that KSE measurements have helped to suggest. And so I think there's a question of just statistical signal noise. How much do you improve the signal to noise? That's one thing. But another question is, can you actually trust any results that comes out of your data? And that's almost priceless in terms of signal to noise. I would sacrifice quite a bit for this. And so if I'm able to say that, with LSST cosmic shear, I can tell you that this is the neutrino masses, or this is how dark energy evolves with more confidence, I think that would be really powerful.
Yeah, thanks for the great talk. I'm curious about the role of CMB polarization in all of this. I know that,
yes,
E modes mix into B modes by gravitational lensing.
Yeah.
But what about through SZ effects and how polarization information is carried?
Yes, thank you. That's a really good question. So today I've really only talked about the group's work on those gas shadow, those scattering effects. There's about as much work from the group on CMB lensing, which I haven't told you about. This is the place where polarization will really, really help a lot. So polarization will help with, primary anisotropies. In a sense, it's almost you have another CMB in polarization, although they're like 20% correlated. And so we have not yet reached cosmic variance on polarization for primordial universe. We roughly will with SO. In terms of the gas and scattering, there are such effects as TSE and KSE. They're analogs in polarization. They're much weaker.
Okay.
So I expect we will be able to barely detect them, not learn too much from them. One idea, though, is because CMB and temperature and polarization are correlated for the primary anisotropies, you can actually use CMB polarization to subtract a bit of your CMB temperature and reduce your noise here by 20%. So marginal gains. The place where the gains I think will be really extreme is in lensing. And the reason that is because if I look at a CMB map, I'm trying to reconstruct lensing from a non-Gaussianity of the map, if you will. If I'm looking at polarization, I have these E modes and B modes, and B modes is basically a null channel. So any B mode I see in this map, it's not foregrounds, is lensing. And that means once your noise in polarization is low enough, lensing improves a lot, signal to noise. It also improves a lot in terms of foregrounds, much fewer foregrounds in polarization. So you basically get a completely independent way to measure CMB lensing that's free of foregrounds. And post-Simon's observatory will actually be the best way to measure lensing. So yeah, a key role of polarization. Thanks for asking. Yes.
Thanks a lot, Manu. I was wondering if you could say more about the neutrino mass constraints independent of dark energy. And then from that, if you have like forecasts on if you could better constrain dark energy now that you've broken that degeneracy and learn.
Yeah, that's a really good question. So I don't want to spoil too much tomorrow, but I'll say a few things. And those things are preliminary results from papers led by Fei, Frank, and Hanui. And several questions we wanted to ask in these papers. One is, where is our neutrino sensitivity really coming from? So there have been a number of papers in the literature recently arguing that it comes from the growth, so suppression of growth from neutrino masses, or that instead it comes from geometry. So this 0.5% contribution to the total matter density, increasing the expansion rate. And so we wanted to know, sort of which one is it? Is it possible to split them so you can measure each independently as a consistency check? And what we seem to find was actually quite interesting. And what we seem to find is that most of the constraining power actually comes from growth. But to get that growth constraining power, you need the geometry from DAISY to measure omega matter. And so at the moment, physically, you're measuring the suppression of the matter power spectrum. But because you're measuring it through lensing, which has an omega matter in it, you need omega matter from lensing. And so the question we then asked is like, okay, you have these different probes of neutrino masses. Is one or the other or both, can they be made independent from dark energy? And our first idea here was, well, neutrino masses have started to matter since redshift 100. Dark energy has only started to matter since redshift 1. Why don't I throw out all my data below redshift 1? And in principle, it's a good idea. It has some challenges, which come from the fact that distances to high redshift care about what happens at low redshift. But you can overcome those. Another challenge, though, is that you really do need this omega matter. And to get omega matter from DAISY, you need the low and high redshift. So at the moment, this is hard to do, to distinguish dark energy and neutrino masses. But I think there's conditions under which you can do it. And that's why we're pursuing now. I think that would be super cool.
Cool, thank you.
Should we just quickly check in online? Any questions online?
And there's Risa as well.
Oh, I'm sorry.
No, that's okay. You mentioned relatively soon potential measurement of 21 centimeter across CMB. Could you say more about like what are the immediate things you think we will learn, and then
Yes.
how do you see the process?
Yes. So I very briefly alluded to this, and for me, my interest in light intensity mapping is really probing this part of the observable universe at higher redshift than galaxy surveys. If you have a galaxy survey, I think you should just use this. It's such a good probe of the large scale structure. And so for me, the point of LIM is to go beyond this. The problem with LIM is that it has those foregrounds that are extremely challenging. And so any large scale structure we're going to learn from LIM will come from cross correlations before O2. Both because the signal noise will be higher and you'll be able to control those foregrounds. But if you want to be at high redshift where you don't have galaxies, what do you cross correlate with? And for me, that's the CMB and CMB lensing. And this was thought to be impossible for a number of reasons. CMB lensing is a 2D map. If you take a limb and you project it to 2D, you've lost almost everything because of those continuum foregrounds. Dylan's paper showed that that's not quite the case, and so there's prospects for doing this. And Tristan's paper with Zishan and me has shown that the high order estimators that we've proposed in the past are actually really, really close to working for Chime and Planck. Really, really close in terms of signal to noise. In fact, the data that's already collected by Chime but not fully reduced might be sufficient for this detection. So for me, the goal really is like zeroth order enable LIM to probe the matter density field at all. And then if you're able to do this, I think that unlocks a number of things. Precision cosmology is perhaps a bit further down the line, but any probe of the matter density field at high redshift would help with a lot of astrophysics.
Okay, we're at the hour. We should probably wrap up. Let's thank Manu again.
That's right. Yeah.